Hello and welcome to our lesson on radical functions and graphs. This is going to be from section 6.1 in our text. In this lesson, we're going to be looking at three topics: how to evaluate radical functions, how to graph radical functions, and find the domain and range of radical functions. And I would like to point out at the beginning of the lesson here that when I say radical, we're mainly going to focus on square root functions. So let's get started. First example, number 41, we have g of x equals the square root of 3x plus 9. And we're going to start with evaluate. So the first thing that I would like to find is g of 0. Now that means to replace every x with a 0 and then work it out and give the answer. So 3 times 0 is 0. So this part will be 0. 0 plus 9 is 9. And the square root of 9 is 3. And so that is the answer to g of 0. What we actually found is an ordered pair, right? So if x is 0, then g of x, remember g of x means y, the y value is 3. So we really found an ordered pair there. Let's do that again. Let's do g of negative 3. Okay, so again, replacing the x with negative 3 and then work it out. 3 times negative 3, 3 times 3 is 9, so that's negative 9 plus 9 is 0, and the square root of 0 is 0. And so again, we have another ordered pair here. If x is negative 3, y is 0. And let's evaluate, a couple more. Let's try g of negative 5. So 3 times negative 5 plus 9. 3 times negative 5 is negative 15. Negative 15 plus 9 is negative 6. And that is no real solution. That is not a real solution, which means there's not going to be an ordered pair for that. So g of negative 5 doesn't actually give us a real answer. And how about one more? Let's do g of 3. So 3 times 3 plus 9. 3 times 3 is 9. 9 and 9 is 18. And guess what? The square root of 18 does not square root nicely. But what I can do is pull up my handy dandy calculator and have the calculator give it in simplest radical form or a decimal if I need it. So probably you're going to need simplest radical form if it says give the exact value, or if it just says to graph, it's a lot easier to plot a decimal number. Got that? So we're going to say 3 square root of 2 which is approximately 4.2. So that does it for the evaluate part. Every one of these problems would take care of the evaluate. Now that we have, what is that, 3 ordered pairs? 1, 2, this is technically an ordered pair. Now that we have about 3 points, let's see if we can produce the graph. So we're going to scroll down a little bit. Got our XY coordinate system, and we're going to plot these points. So we've got 0, 3, negative 3, 0, and if x is 3, y is 4.2. And so that's going to be about there. Now, it turns out that the shape of a radical function is always, well, what I call a swoosh. it's going to have a starting point, and in this case, it's going to swoosh to the right. The swoosh is not the technical term, but that's kind of what it looks like a Nike swoosh. Swoosh. Anyway, there's our graph, and that is the complete graph, and I will explain why I know it's the complete graph in just a second when we talk about domain and range. Okay, so now at this point, we're going to do domain and range. Since our function is a square root function, that means it has an index of 2, we know that this radical function will have a restriction. And the restriction on a square root function says that the radicand, which is the stuff under the radical, must be greater than or equal to 0. That is the restriction on a square root function. So we're going to come down here and we're going to say, okay, 3x plus 9 must be greater than or equal to 0. And then we're going to solve that for x to find the restriction. Moving the 9 over, 3x greater than or equal to negative 9. And then divide both sides by 3. And that's going to give us x is greater than or equal to negative 3. Now that is the restriction. If I want to make it the domain, I'm going to add a brace, another x, a vertical bar, and a brace. This notation is called set notation. I'm also going to write that in interval notation. So if you think about what this says, it says x must be greater than or equal to negative 3, which means everything from negative 3, including negative 3, to infinity. Greater than or equal to negative 3 means everything from negative 3, including negative 3, to infinity. And so there is our interval notation. Now, since the domain indicates that we're going to begin at negative 3 and go forever to the right, that means the graph should start at negative 3 and go forever to the right. So that means I do have a complete graph from beginning to end, because the domain should represent where the graph exists. Now, let's talk about range. The range are the values that y can be, and the y is how high. So since we want the y's, we're going to scan from bottom to top, and we're going to figure out where does this graph start existing, and then where does it stop existing. Okay, so it's going to start on the x-axis, which is at a y value of 0, and then notice that it's going to increase forever. So the farther this goes to the right, the more it's going to increase upwards. So the range is going to go from 0 to infinity. And remember, this is interval notation. If you have to have set notation for whatever reason, that would be the set of all y such that y is greater than or equal to 0. So there's your set notation also. For the remaining examples, we're going to look at evaluating simply to get ordered pairs so that we can graph and then find the domain and range. All right, so let's start with g of 0 again. And that's going to be 8 minus 4 times 0. And then I need to work that out and give the answer. So 4 times 0 is 0. 8 minus 0 is 8. And 8 does not square root nicely. So if you do not have a calculator and you need to write it in simplest radical form, what you need to do is break that down into factors, one of which can square root. So I know that 8 can be written as 4 times 2, and 4 can square root. And that means it can come out from under the radical as a 2 because the square root of 4 is 2. And simplest radical form here would be 2 square root of 2. Next, let's find g of 2. 8 minus 4 times 2. That's going to be square root of 4 times 2 is 8. 8 minus 8 is 0. And the square root of 0 is 0. And if you're starting to wonder, where am I getting these numbers from? I'm just making them up. Okay? You can pick anything you want unless they give you values to evaluate, and then you need to plug in the numbers they give you. But as far as graphing goes, I'm just randomly picking values of x, plugging it in, and see what I get. Okay, so I'm going to go 3 next. 8 minus 4 times 3. Well, 4 times 3 is 12. 8 minus 12 is negative 4. And remember, negative numbers won't square root. So that is a no real solution. That's not going to actually produce a point on the graph. And so at this point, I've got only 2 ordered pairs that I can plot. So let's do one more. Notice what happened there. The x's, I went 0 and then 2 and then 3. So I was increasing my x's, and I hit a point at which the numbers were not square rootable. So what I want to do at this point is go backward. So maybe I need to pick 1 or a negative number. I need to go back down in the x direction. So let's try 1. Here we go. 8 minus 4 times 1. 4 times 1 is 4. 8 minus 4 is 4. Hey, and that square roots nicely. So that's going to give us a 2. And normally you need about 3 good points. And you do definitely need the starting point. Like we had back on the previous graph, you have to have the point at which the graph begins. And I think we do have that. And you can tell for sure when you get down and do domain and range, once you figure out where your graph has to begin, you can make sure you include that point. All right, so let's go to the graph. And I've got ordered pairs of 2 and 0, 1 and 2, and then I've got an ordered pair 0, 2 square root of 2. So I'm going to need to know the decimal approximation for that so that I can plot it accurately, and for that we're going to use the calculator. So I'm going to type in square root of 8. That's probably the easiest way to do that. Equals, of course, there's my 2 square root of 2, and then the SD button. That's about 2.8. So 0 would be up at 2.8, which is almost 3. Now, remember that I said once I hit 3, I got a no real solution. So this graph is actually going to swoosh to the left. This one's going to swoosh up to the left. And I'm going to prove it when I do the domain. So now finding the domain, remember a square root function has a restriction, and the restriction is that the radicand has to be greater than or equal to 0. So we're going to say 8 minus 4x greater than or equal to 0, and then we're going to solve for x. I'm going to move the 8 over, which is going to make it negative 8. And then if I divide both sides by negative 4 to get rid of the negative 4, I'm going to need you to remember that when you divide by a negative number, the inequality has to flip. And a negative over a negative makes a positive. So there's the restriction. Now we need to write it as the domain. So that's going to be the set of all x such that x is less than or equal to 2. And that is verified from the graph. Do you see that? That the graph stops at a value of 2 and it goes forever to the left. That is less than or equal to 2. So now I know I have a complete graph. And now we can do the range. Okay. So remember, the range are the values that y can be going from bottom to top. I see that the graph begins at the x-axis, and at the x-axis, y is 0. So the range is going to start at 0, and it's going to finish at infinity because it's going to increase forever as it moves to the left. So there is the range in interval notation, and I got the domain in set notation. So let's go ahead and rewrite the domain in interval notation. That would be everything from negative infinity up to 2, including 2. So there's the domain in interval notation, and then the range in set notation would be the set of all y such that y has to be greater than or equal to 0. And that pretty much covers another example of how to evaluate, graph, and find the domain and range. Okay, next, number 34. This is the last example we're going to do in this lesson that looks at evaluate, graph, and domain and range. Some of you may be wondering, how do you know what x's to pick if you're just having to pick x's to find points on the graph? I can give you a hint for that. Okay, let's assume that you don't know what x to pick and you would like to figure out what a good starting x would be. Well, to start with, making the radicand equal to 0 should give you the starting point of your graph. So you want to ask yourself, what x should I pick to make the stuff under the square root 0? And that'll give you the starting point of your graph, and that value is 1. So to evaluate, here we're going to have the square root of 1 minus 1, which is 0. 2 plus 0 is 2. And so that gives us the initial or starting point of the graph. And then you want to increase by 1. That's probably a good rule of thumb. So next, let's just go to 2. 2 plus square root of, this time 2 minus 1. 2 minus 1 is 1, and the square root of 1 is 1. And then adding, we get 3. So again, remember, I'm finding ordered pairs. This is an x comma y, an x comma y, and I probably need one more, and I'm going to jump up to 5. And if you're going, whoa, slow your roll, how did you get 5? Well, let me explain. Remember, we're doing square roots. And so what I would like to have is numbers that square root nicely, like 1, 4, 9, 16, 25. You get the idea? I want numbers that square root nicely. So if I think ahead, I come up with 5 as a good next number, because 5 minus 1 is 4, and 4 will square root. So if you're careful and you think ahead, you're going to get nice whole number answers. Here we go. 5 minus 1 is 4, and the square root of 4 is 2. 2 plus 2 is 4. Now, let's go to the graph. So the first ordered pair would be 1, 2. Next ordered pair would be 2, 3. And the next ordered pair would be 5, 4. So 1, 2, 3, 4, 5, 4, like so. And did you hear me say a second ago that every square root graph is going to make a swoosh? And so I can see that this graph is going to swoosh to the right, like so. I've got my starting point at 1. This graph is going to go to infinity and beyond. Let's find the domain and range. Now, remember, for the domain, the restriction on the square root function says that the radicand must be greater than or equal to 0. And so I'm going to say x minus 1 greater than or equal to 0. And I'm going to solve for x. Moving the negative 1 gives me x is greater than or equal to 1. That's the restriction. To write it as the domain, you have to say the set of all x such that x is greater than or equal to 1. And then if you don't need set notation, at that point you can write interval notation, because this graph begins at 1 and goes to infinity. And do you see how the graph verifies that? That this graph begins at 1 and it goes forever to the right. Now, how about the range? Remember, the range are the values that y can be. Notice that this graph doesn't exist below 2. Y equals 2 is where this graph starts existing, and then it's going to increase upward forever. So the range is going to be everything from 2 to infinity. That would be interval notation. If you need set notation, that would be the set of all. That was a terrible brace. That would be the set of all y such that y is greater than or equal to 2. Bam, and there's your set notation. And that's going to do it for that example right there. For our last example, number 91, here we have a what I would call a radical rational function. This is effed up, dude. Do you see it's fractioned up? And it's got square roots top and bottom. The instructions say find the domain. So if you're going to find the domain, that means the values that x can be, you're going to have to gather together all of the restrictions and then look at what x can't be to determine what x can be. Now we know that for a square root, the stuff under the square root, which is the radicand, must be greater than or equal to 0. Got that? So we're going to have a restriction from the numerator, x plus 3 greater than or equal to 0, and we're going to have a restriction from the denominator. Now, if you remember, the denominator of a fraction cannot be 0. So since the denominator contains a square root, we know that the stuff under the square root must be greater than or equal to 0. But since it's in the denominator, it cannot be 0. So you're going to have to remove the equal to part of that restriction. Okay, so that's going to be the restriction from the denominator. 2 minus x must be strictly greater than 0. And now if I solve both of these inequalities for x, I will have the restrictions for the function. All right, here we go. Moving the 3 over, we see that x must be greater than or equal to -3. And on the other one, I'm going to move the negative x over, which is going to say 2 is greater than x, and then I'm going to flip that around. So if the arrow points to the x and I flip it, it has to still point to the x. The inequality, if you flip it around, has to flip also. So that's going to say x is less than 2. Now, just for me personally, if I've got a compound inequality, since we have the word and, this is a compound inequality, the easiest way for me to figure out the domain is to look at a number line. So I've got two critical points. I've got -3 and 2. -3 is a solid dot. 2 is an open circle. The x is greater than or equal to -3 is going to shade to the right. X is less than 2 is going to shade to the left. Now, both of these conditions have to be met. That's why I use the word and, which means I'm looking for the intersection, which is where the shadings overlap. And they overlap in the middle. So the domain in interval notation would be everything from -3. I'm using a bracket because it's a solid dot, up to and not including 2. That would be the domain for that radical rational function. And that's going to do it for this lesson. So if you have any questions or comments about anything that I've covered, feel free to leave that in the comment section below, or you can text me. And thanks for watching.